In today's video, we will be looking at exponential functions for growth and decay, and what is growth and decay. So we have our foldable here. This, of course, is where our glue will go. So we turn it over to the other side. We're going to fold it to the middle and then cut along the dashed lines so that we have some little flaps. So here's our foldable. We will be looking at what is an exponential growth or decay function first. So we open up this flap and we see an example of growth and decay. We have an exponential function that is in this form. A or B cannot both be 0. B determines whether or not you have growth or decay. We can see from the graph here that it is increasing from left to right. This is growth. And if you look at B, B is bigger than 1. So whenever you have a function, you can tell it's growth because B is bigger than 1, or you can look at the graph and tell that it's an increasing function, so you have growth. For decay, we look at the function, then we look at the graph, and we see that it is decreasing. And if we look at the function itself, we look at B. B is a fraction. So anytime we have B being between 0 and 1, that means it's a fraction. And if B is a fraction, we have decay. So we will look at writing an exponential model. And in this case, we're going to have to deal with a rate of change. So that means we're going to have to change up B just a little bit. So let's look at the first example. You buy a commemorative coin for $110. Each year, the value of the coin appreciates by 4%. Appreciate means that it grows. So what we're going to do is use 1 plus the rate because it's going to appreciate. So we're going to go up by 4%. So we're going to be adding 4%, and then we're going to have A times B raised to the X. So B this time takes the form of 1 plus R. So A in this case is 110. R is 4%. So you take 4 and divide it by 100. So if we do that, we get the decimal 0.4 or 400ths. Simply replace these into your formula. 1 plus, and we have a decimal 0.4. And this time, what X is X is representing time, and they want us to use T for time, so we're going to use a T as our variable up here instead of the X. Then we're going to simplify. We end up with 1.04, or 1 400ths, all raised to the T power. And this, because B is bigger than 1, is growth. So let's look at the second example. In this one, we're going to buy a stereo system for $780. So our initial is $780. That's A. Each year, so we're going to use T again instead of the X. Each year, the value of the stereo depreciates by 5%. So our rate is going to be 5 over 100, which is going to be 0.05. So with appreciation, we added. But with depreciation, we're going down. So instead of adding, we will subtract that rate. So now we substitute our values. A is 780, R is 0.05, and X is actually going to be T for time. Simplify. And here is our decay function for this situation. Okay, so let's solve an exponential growth word problem. Excuse me. A town had a population of 48,000 in 2011. Then the population increased by 8% per year for the next 5 years. Write an exponential growth model for the town's population over the 5-year period. Use the model to find the population in 2014. So we're going to use P for population is going to be our initial amount, and because it increased, that's an addition, so we do 1 plus R, and we're going to raise that to the X power. So A is equal to 48,000. R is equal to 8%, so 8 divided by 100 is 0.08. And our X is in terms of time, so we're going to call it T. Now we have to substitute our values in. But we have to do two things. They want us to write an exponential growth function for the town's population over the 5-year period. So A remains the same. Our rate remains the same. And we're just going to call this X a T for now. Simplify. Okay. Now it says to use the model to find the population in 2014. So 2014 is actually 3 years away, so our T ends up being 3. So we have P equals 48,000, 1.08 raised to the 3rd power, and that, when we put it in the calculator, is going to yield 60,466 people. So in 3 years, they expect the population to be a little over 60,000. So that was a growth there of 8% over 3 years. Now we need to solve an exponential decay word problem. Between 2010 and 2014, the profits of a business decreased by approximately 0.5% each year. In 2010, the business profit was $1.2 million. Write an exponential decay model showing the business's profit in year T. What is the profit in 2014? So this time it's a decrease, so we're going to say A times 1 minus R, all raised to the X power. So A in this case is 1.2 million, so that's 1,200,000. Our rate is 0.5%, so that's 0.5 per 100. That is going to give us 0.005. And then X, of course, is our time. So it says write an exponential decay model showing the business's profit in year T. So X is going to be T. So we have P equals A, which is 1,200,000 times 1 minus 0.005, and we're raising that to the T. So 1 minus 0.005. Okay, so we're going to get P equals 1.2 million times 0.995 raised to the T power. So there's our exponential decay model showing the business's profit in T years. Now they want to know what the profit was in 2014. From 2010 to 2014, your T then is going to equal 4. So we take P equals 1.2 million all raised to the 4th power. When you put that into the calculator, your profit is going to be $1,176,179.40. So this is money, so we want to make sure that in our final answer we put some money. So this is, of course, because it's money, we're going to round to the hundredths place. You're going to get a 0.401 here when you put this into the calculator. And that is the amount of profit they had in 2014, which is, of course, a decrease. They're still making money, but it is a decrease. Okay, so there is solving growth and decay, so now we need to graph. This is strictly a calculator issue here. So we're going to go to y equals, because f of x and y are the same thing. We're going to put this in exactly as we see it, and this time we're going to be subtracting 1. So what that's going to do is move our whole graph down a little bit. So let's go ahead and look at the table of values, and let's get that information put in. For -1, we're going to get -0.3 repeating. For 0, we're going to get 1, and for 1, we're going to get 5. So what that looks like here is f of -1 equals 2 times 3 to the -1, subtract 1. For this one, we have f of 0 is going to be 2 times 3 to the 0 minus 1. And f of 1 is going to be 2 times 3 raised to the first power, all subtract 1. So let's go ahead and graph these at 0. And that's an easier one for me to graph. And we'll go ahead and graph that 0, 1. At +1, I get a +5, which is right here. And then at -1, I get -0.33. Well, 0.33 is basically a third, or somewhere around 3/10. So we're going to put that right here. And because we have this -1, our asymptote has changed from being the x-axis to being this -1, because it's gone down 1. So this curve comes this way, and it never crosses that asymptote. This curve goes up pretty high. So I'm going to go ahead and draw in the asymptote. So our asymptote is at y equals -1. Okay, so we basically put this into the calculator. We looked at the table and found that when x is -1, we get -0.3 repeating. 0 gives us a 1, 1 gives us a 5. We know that if we didn't have this subtract 1 there, if that wasn't there, that our asymptote would be 0, that it would not go, it would never get to the x-axis, it would never go below it. But because we subtracted 1 from the y value, that whole function has been dropped down 1 unit, so that makes our asymptote here at y equals -1. Okay, so this is a growth function because it increases from left to right. So let's look at the last one here. So we have, for our function, we have 4, then we have 1/2, and off of y equals, we'll go ahead and do this as a fraction there. And we're going to raise that to the x power, and then we're going to subtract 3. So when we look at the graph for -1, or sorry, look at the table, for -1 we get a 5, for 0 we're going to get a 1, and for 1 we're going to get a -1. So let's go ahead and fill out g of x. So g of -1 means we are evaluating the function at -1. We're going to get 4 times 1/2 raised to the -1 power, and then we're going to subtract 3 from that. For g evaluated at 0, 1/2 is being raised to the 0 power. And then g evaluated at 1, because x is 1, we get 4 times 1/2 raised to the first power minus 3. So let's graph these ordered pairs. At -1 we get a +5. At 0 we get a +1. And at 1 we get a -1. Now, because of this -3 right here, we know that our asymptote is going to be at -3. If there's not a number being added or subtracted, then you don't have to worry about that. But here's our asymptote. I'll write that in here. So whenever we start connecting our dots and drawing our curve, we know which line we are approaching. So here's our curve. And this curve is just going to approach that -3. And this is a decreasing curve from left to right, so we have decay. So here we have examples of what it is to be growth and decay, some examples of how to set up the equation if B isn't given to you, if you have to figure it out using a rate, and what to do when you have just a function, and how that asymptote might change given whether you're adding or subtracting to the function itself.